Okay, so this is NCCER Instrumentation 2 Module 9. Today is 2/9/24. This is just a straight through lecture on Module 9 of Instrumentation 2. So, protective measures for instrumentation. Section 1. Page 1, you've got a bunch of trade terms that'd be worth reading through. I know teaching this class in Southeast Louisiana, electrical heat tracing is not usually something that we run across, but it is in other parts of the a lot of other parts of the country with a lot colder climates than we have here. There's some trade terms that you should probably know. Constant wattage cable, you should know. Currents transformer, you've seen over and over again. You should know what the dew point, frost line, stuff like that is. We're going to talk about different types of cables, and they have those like the self-regulating cable as we go through this section, along with like the power limited cable, mineral insulated cable. We'll go through those as we're going through this section. So page 2 is where I have my first highlights. My first highlight is in the first paragraph, second sentence. The most common method of applying heat to piping system components is with electric cable heating systems, otherwise known as electrical heat tracing systems. All this heat tracing is if you look on page 3, you can see you're just you got this figure 1 up on the board, and you can see these wires that run alongside the pipe with strapping and thermal insulation tape or glass tape. You have to go around valves in certain ways. That way you can take the heat tracing off without taking all of it off. But it's pretty much just a couple of wires that produce a lot of heat that keep your pipes from freezing. The immediate next sentence is also highlighted. Electrical heat tracing is used to prevent pipelines from freezing, to maintain process fluid temperatures and flows, and or to prevent condensation in pipelines. Out to the side of that, I wrote to eliminate need for thermal insulation. You still have to have that thermal insulation. Usually you have heat tracing on the inside, and then you put your thermal insulation around that to hold the heat in. Heat tracing does not eliminate the need for insulation, thermal insulation. Electrical heat tracing application, right-hand side of page 2, first full paragraph, first sentence, the one with viscosity is highlighted. Broad temperature control, so wide range control, is used to maintain the viscosity of process fluids in order to keep them flowing. So it's not worried about if there's like it turns into a slurry or anything like that. Like, it's just to keep things from freezing all the way up. Next paragraph, first sentence is highlighted. Narrow temperature control is used to keep process fluids with a narrow temperature range to maintain fluid viscosity and to prevent degradation of the fluid composition. So this is, they have to keep the temperatures within a narrow range. So you got broad range, just keeping stuff moving. Narrow range, more specific to the viscosity of the fluid, and you have to let stuff move for whatever the specific application is. Immediate next sentence after that is also highlighted. Typical applications for narrow temperature control are sulfur, acrylic acid, food syrup, and sugar solution lines. So stuff that has to stay at certain temperatures in order to move it at the pace that the plant or company wants it to move. Page 3, heat tracing system power distribution. So this is the power that goes to this stuff. Most of the time this stuff is outside, but sometimes it's inside. And so this is just the power getting out to the heat tracing systems. So first paragraph, about right in the middle of the paragraph, I think it's the third or fourth sentence, the main circuit breaker is used to disconnect power from the panel board and to protect the panel buses, transformer, and the wiring between the transformer and the distribution panel. That's just saying you have a main circuit breaker, disconnects power to the whole panel board. Next sentence. You got two highlights coming from the next sentence. The branched circuit breakers are ground fault interrupting circuit breakers. GFCI. These are GFCI circuit breakers used to apply the operating voltages to the power connection boxes of one or more heat tracing systems. We'll talk about how these GFCIs, normally a GFCI for like a plug in your house is going to open up between 3 and 5. If there's a difference between 3 and 5 milliamps, they will open up. These have a larger range. Like these aren't made to protect personnel, they're made to protect the equipment. So they're a little bit different and they're on the circuit breakers. The immediate next sentence is an online test question. The typical supply voltages are 120, 277, and 208, 240 volt AC. That's for these heat tracing systems. Heat tracing system cables. So you have the 3 different ones right there that are blue highlighted. Self-regulating, power limiting, and mineral insulated. You need to know the differences for these tests. It goes through each one and you'll have highlights for each one. It's 131, the self-regulating cable. First sentence is highlighted. Self-regulating cables are used for applications that require a heat output that varies with changes in temperature of the air or other medium surrounding the cable. So this cable will self-regulate its temperature based on the ambient air temperature. Immediate next sentence, immediate next 2 sentences, you got 2 more highlights coming from. Top right of page 3, a self-regulating cable increases its output in response to a decrease in ambient temperature. Conversely, it decreases its output with an increase in ambient temperature. Moving on to pages 4 and 5, they show like the connections and the different parts of the cables and stuff like that. For whenever you are in class, you'll see these cables with the different jackets and stuff. But pretty much it's 2 wires that run through the whole thing, and then it heats up. This whole slide talks about how the self-regulation works. It's all about the material that's in between the 2 cables and how it can get hot or cold depending on the ambient temperature. Not a bad thing to read through, but no highlights on page 4. Page 5, power limiting cables. So 132 power limiting cables. Not a bad idea to read through these, but I do not currently have highlights in 132. 133 mineral insulated cables. No highlights on page 5 or page 6, but I expect online test questions to come from both of those sections. You should know the difference between the 3 different types of cables. 134 long line cable installations, page 6. First paragraph, second sentence through the end of the paragraph is highlighted. Some applications may involve cable lengths ranging between 1,250 and 5,000 feet that are powered from a single source. For many of these long line applications, specifically designed self-regulating and mineral insulated cable systems are used. So if you're using if you need a long run of this heat tracing, you're only going to use the self-regulating and the mineral insulated cables. 140. This is going to talk about the heat trace system controls. So you've got the 5 different types of controls on page 9. You've got the self-regulating, ambient sensing, proportional ambient sensing control, line sensing control, and then the dead leg control. So it's going to go through each of those. Some I have highlights on, some I don't. 141 self-regulating control, first sentence is highlighted. A self-regulating control system uses the built-in properties of the self-regulating heating cables to maintain the desired pipe temperature. That's going back to the inside of this material that's on the inside. You just put power to this and it regulates itself. It's all about the material that's on the inside. The ambient sensing control, nothing highlighted in that. 143 proportional ambient sensing control. Second paragraph, so last paragraph on page 7, first sentence is highlighted. A PASC, proportional ambient sensing control, uses a programmable electronic controller connected to a remote temperature modules and a contactor control modules to regulate one or more heat tracing cables. So that's just saying this has a contactor that can turn on and off based on the temperature outside. It's just turning the cables on or off based on the temperature. Moving on to page 8 and 9, line sensing control 144. So that would be, I don't think I have a picture. The picture on page 8 and figure 9, that's what you're going to use for the line sensing control. First sentence has a couple of highlights come out of 144. A line sensing control system uses a mechanical thermostat or electronic controller to measure the actual pipe temperature. So figure 9 shows that it has a sensing bulb that's going to measure the actual temperature of the pipe. Whereas like using the ambient sensing thermostat, which is what's on the board at the top left of your page, that's measuring the ambient temperature outside. The line sensing is going to measure the temperature of the pipe itself. The sentence that splits the columns is an online test question, 144 on page 8. Line sensing controls are used in narrow temperature maintenance situations because they provide the most direct and highest degree of temperature control and consume the least amount of energy. Think about it, if you're just controlling your temperature of your pipe and not just the outside ambient air, your pipe might hold more heat than the outside air, so you're going to use less electricity based on where you're sensing for your temperature. 145, dead leg control, second sentence is highlighted. The dead leg contains a system fluid in a permanent no-flow condition. So essentially what they do is they take a pipe, fill it up with the fluid that they're moving, and they're just using that one piece to sense the temperature, and then they're controlling the whole system based on that one component. Heat tracing system monitoring. So this is monitoring the system as a whole. Ground fault monitoring, 151 on page 9. Last paragraph on page 9, second sentence is highlighted. However, the function of the equipment ground fault circuit breakers is to protect the equipment rather than personnel. So that's what I talked about a little bit earlier. These GFCIs are protecting the equipment, not the personnel, so they're not going to react the same. Immediate next sentence talks about that, which is highlighted. The equipment ground fault circuit breakers used in heat tracing circuits are designed to trip at 30 milliamps rather than at 5 milliamps like GFCIs used for personal protection. They are slightly less sensitive. So these, a lot of times you might have in your house like a GFCI, like everybody's seen like a fridge or something trip a GFCI where you reset it and it's kind of these ghost trips. These GFCIs that are used to protect this, they want to use a GFCI because this stuff can be in wet areas, and if you have a lot of moisture build up, like you don't want, obviously moisture can conduct electricity, so you don't want electricity running through that, but they're not as sensitive, so they're not going to trip with a smaller milliamp reading. It's going to use a 30 milliamp. It's going to see 30 milliamps before it trips. Page 10, 152, continuity monitoring. The first sentence sentence is highlighted with two. You'll have two questions come out of first sentence of 152. Continuity monitor verifies that the voltage is present at the end of the termination. Key in on that. Voltage is present at the end of the termination of a heat tracing cable run. This can be done by using an end of circuit LED that remains on when the circuit is operative and shuts off if there's an open in the circuit. So all that is, you've got a light. I don't have a picture of that one, but they show a picture on page 10, figure 11. It just shows the end seal with a light. So if everything's good, the light will be on. If something happens, the light turns off, so you can just see if the whole system is on or off. They have current monitoring, which is what's on the board up here. Which is ground fault monitoring. You're using a current transducer to monitor the current running through the cables. Nothing highlighted in 153. Going on to page 11, 154, temperature monitoring. First sentence is highlighted. Temperature monitoring systems continually monitor the temperature of the pipe with resistance temperature detectors, or RTDs. See up here on the board, or at the bottom of your page 11, you've got an RTD on this pipe, and then the heating cable. So the RTD senses the temperature of the pipe, and then sends back to the distribution panel, which turns on and off the power connection based on the temperature. Moving on to page 13, we're in the 155 typical heat trace system operation. So you read through this talking about how the system operates. So you've got a controller on page 12 that can turn on and off heat tracing. The last sentence before 160 is highlighted. Use of power line carrier technology allows temperature and continuity data to be sent to the controller without running additional wiring to the sensor locations. I've talked about this in previous classes. I know when I was in college, they had this new technology that can run through power outlets. So you could actually plug a TV into a power outlet, and then you could also send a different signal on a different frequency. We run at 60 hertz for our power, but at a different frequency they could send a different signal, so you wouldn't have to have like a separate connection for your TV. I don't know where that technology went, but they're using it for this. So they're saying they can send temperature readings at a different frequency on the power line, so that way you don't have to run a separate communications wire. Pretty cool technology. Installation guidelines 160. You can see up here on the board how you're supposed to wrap a valve, and like I said before, if this valve ever has to be serviced and pulled out, you can, instead of pulling the whole line out, you can loop this around to where it's got the valve heating up, but whenever you have to take it out of service, you can just undo the strapping, and this will pull out with just the slack being left. Same thing for a flange. Like, you can just loop this, and then if you ever had to undo this, you can get in that flange without having to undo all of the heat cable. The highlight that I have on page 13 for 160 is on the right hand side of the page. That second bullet point in the top right, second to last sentence. Typically 2 feet of cables added for each electrical power connection, splice T, and end seal. So you're just adding on, it's just extra cabling because a lot of this stuff you can cut to length and splice, but that's just extra cabling for those purposes. Moving on to page 14, more considerations when running heat tracing. The third bullet point on page 14, first sentence is highlighted. Avoid overlapping the heat tracing when using a cable that is not self-regulating. So do not overlap stuff if it is not self-regulating. First bullet point on page 15, first sentence is highlighted. Heat tracing cold leads. The section of the power wiring leading to the pipe surface must be positioned to penetrate the insulation in the lower 180 degree segment of the pipe. All that's saying is, if you look at, I think they give me the picture, this heat tracing comes in from the bottom, and that's because, like we've said, all the pipes still have insulation on them, and if we enter from the top, that creates a leak point. By entering from the bottom, water shouldn't go up or stuff like that, so there's less of a chance of this filling up with like rainwater or something like that. So you enter the bottom half of the pipe with your cabling when you're installing. Second to last bullet point on page 15 is highlighted. Sensors must also be located 3 to 5 feet away from a heat source or heat sink in the system. So that's just saying you don't want to have inaccurate readings, so you want to keep those things away from the heat source for your sensors. You got section review 1 on page 16. I'm going to move directly on to section 2. Section 2 is on a non-electric protection scheme. So this is not using heat cabling. This is using different forms of keeping pipes from freezing. So you have the things you're going to need to note. you need to know the difference between burst protection and freeze protection in your trade terms. Burst protection and freeze protection. A lot of the other stuff you've probably heard of before. They'll talk about glycols and inhibitors. Glycol is used in like your antifreeze system. It lowers the freezing point. It's a lower freezing point than water. So if you get to 32, that's not going to freeze. That's how like your cars and stuff, your antifreeze in your car is made up of glycol, so that your car radiator doesn't explode when it gets below 32 degrees. It can go, that glycol can go a lot lower, so they use that to keep stuff from freezing. And then like steam traps, you should know what a steam trap is. Takes the water out of steam. But that's the cheaper way of keeping pipes from freezing is heat tracing. I need to go on to my next PowerPoint. So steam tracing, steam heat tracing 210. So no highlights on page 17, going on to page 18. We talk about different ways of using steam tracing. So 211 talks about the jacket and externally mounted convention steam tracing system. So that's mounting stuff on the outside of the pipe to keep stuff from freezing. Nothing highlighted in 211. 212, conduction tracing using heat transfer compound. Second sentence in 212 is highlighted. When this conductive paste-like material is applied to a single bare tube or small pipe tracer, it can replace multiple bare tracers and can closely parallel heat delivery rates of a fully jacketed pipe. Yep, so you're just using conductive paste. You can kind of see that paste in figure 17 or up here on the board. They have this heat transfer compound used to transfer, that's the black stuff, transfer this heat from the steam pipe into the actual pipe. Steam tracing today, 213, page 19, first full paragraph or that little middle paragraph. First sentence has two questions come out of it. The least costly alternative and simplest to install is the channel 2 conduction steam tracing system, which is what's up here on the board. This is the cheapest version of heat tracing to install. Moving on to page 20 and 21, they do go through the accessories. I don't have anything highlighted in 214. Going on to page 21, 220, chemical freeze protection. 220. Second paragraph, first sentence is highlighted. Glycols and inhibited glycols are the most commonly used winterization chemicals. Skip a sentence, and I've got the third sentence highlighted. The purpose of the inhibitors, the ethylene and propylene, is to limit the corrosion that occurs inside the pipe, inside of the piping. So inhibitors inhibit corrosion. Glycols keep stuff from freezing. Next paragraph, first sentence is highlighted. In a system where heat transfer efficiency is a concern, ethylene glycol is a much better choice than propylene glycol due to the difference in viscosity. I think ethylene glycol is what's used in cars and stuff like that. Pretty sure it might talk about that. But it does talk about ethylene glycol is toxic. I know, so you want to watch that. Like, I'm pretty sure that ethylene glycol is what's in the your antifreeze for your cars and stuff. I know when I was growing up, got neighbors across the street had one of the basketball hoops with like the counterweight at the bottom. You filled with water or something, and he'd fill it up with water. But to keep it from freezing, he'd put some antifreeze in it. Well, it froze, it broke, melted. Antifreeze was on the driveway. Their dog drank the antifreeze or licked up some of the antifreeze because it's got this sweet smell and stuff like that. Dog died. Bad day for the neighbors, stuff like that. So you want to watch you want to watch these ethylene glycols and stuff if you're using antifreeze or whatever. Like if you spill that stuff on the ground, like soak that ground down, dilute that ethylene glycol so nothing's getting into it. 221, burst protection versus freeze protection. It just talks about the difference between the two, like they're close, but not exactly the same. Second paragraph at 221, second sentence. In a system using chemical additives to provide burst protection, the concentration of additives is lower, thus a slush mixture forms inside the system and is transported through the piping. So with just burst protection, you don't have to have as much chemicals. So this isn't keeping the same viscosity of fluid, this is just making sure the pipe doesn't burst. So you're adding less of a concentration of glycols and stuff. For freeze protection, you're adding more of a chemical concentration to keep a more freely flowing liquid, whatever you're transporting. Going on to page 22, still in section 221, the paragraph that continues on into page 22, I think it's the second to last sentence is highlighted. Using fluids with excessive glycols greatly reduces system heat transfer efficiency. This must be considered when determining the correct concentration to use. Just talk about getting the concentrations together for these. So they actually have for freeze protection, burst protection, and what percent fluid concentration is required at what temperature. That's your picture at the bottom of page 22, table 2 down there. 222, preparing a system for chemical addition. The first sentence is an online test question. When preparing to add winterization chemicals to a system, the most important step is to first ensure the system is clean. Making sure the system's clean, step number 1. Skip 2 sentences all the way in the bottom left of 22. I got another sentence highlighted. Chloride ions found in acid cleaning solutions must also be cleaned out. Chloride ions found in acid cleaning solutions must be cleaned out. 230, going on to talking about insulation of piping. We got different types of insulation on page 23. First paragraph on page 23, third sentence is highlighted. The lagging, often made of a painted canvas, is a protective and confining covering placed directly over the insulating materials. So the lagging is just the covering of the pipe system. You see these are covered in like reusable blankets, so you can take these off and put them back on. You can have stuff, the insulation can be made of a bunch of different materials. 231, fiberglass and mineral wool. Everybody's probably messed with fiberglass insulation in their attics or walls or something like that. It's fiberglass, has a good insulation rating. Usually they're marked with an R factor. Nothing highlighted in 231. 232, calcium silicate. The first 2 sentences of 232 are highlighted. Calcium silicate is a rigid, dense material used exclusively for applications above 250 degrees Fahrenheit. This insulation material has been a standard for high temperature applications for many years. So you need to remember, calcium silicate is for high temperature applications. So keeping temperature out of pipes. Perlite 233, page 24, last sentence is highlighted. Is it usually applied with metal bands and covered with a metal jacket? So that's usually where I've seen that. It's like you've got figure 19 at the bottom of page 24. You got the blankets covering up the valves. That way you can cut those connections off, unwrap the valves, and service them as needed. But the rest of the pipe is still covered in that metal. That metal covering has insulation on the inside of it. 234 talks about reusing insulated blankets. You can redo that, but it's kind of common sense how they can reuse those blankets. 235, thermal insulation used with heat tracing systems. First paragraph, last sentence is highlighted. In some cases, the trace line is wrapped with aluminum foil, then covered with insulation as the foil increases the heat transfer. So some of these have aluminum foil coverings, then the heat tracing, the aluminum foil helps distribute the heat. 240, miscellaneous protection devices and techniques. Moving on to page 26. Nothing highlighted on page 25. You've got the pigtail pressure gauge siphons. So that's the what's up at the top. Might have this on the next. What am I doing? So pigtail pressure gauge siphons, that's the picture in figure 23 at the top, right at page 26. Second sentence is highlighted. The steam condenses and collects inside the pigtail portion of the siphon. The condensate prevents the steam from coming in direct contact with the pressure instrument. So you can separate your pressure instruments with a gauge siphon. 242, dampeners or snubbers. We've talked about these before. First sentence is highlighted. Dampeners or snubbers are installed at the input side of the pressure element to alleviate multiple rapid pressure changes in the input of the device. Those are shown in figure 24, so you put those on, keep people from slamming pressures on and off all the time. Chemical seals, 243. Talked about these a little bit. The last full sentence on page 26 is highlighted. The diaphragm assembly detects the pressure of the process and transmits it to a safe fluid on the opposite side. So if you have the chemical seal right, this valve right here has a chemical seal. There's a diaphragm in here. So it might be, just say we have acid. Acid is pushing up on the bottom of this, hitting the diaphragm. The diaphragm separates this from an inert fluid that actually pushes up into this board-on tube or whatever type of connection this pressure vessel is. So the diaphragm is what separates the chemical from it protects the instrument from whatever chemical is in the process. 244, protecting instrumentation during construction. Page 27, top right of the page. All the way in the top right, kind of the end of that paragraph is highlighted. Into that first paragraph of 244 at the top of 27. Instrumentation components should be kept in their original packaging until they're ready for installation. Often this packaging will contain padding, protect components during shipping and storage. Yes, until you're ready to get the instrumentation out, leave it in its original packaging. Skip a paragraph, and I've got the next paragraph, the whole thing highlighted, online test question. If workers are welding or using torches or grinders in the area where instrumentation is installed, they must use protective blankets to prevent weld splatter or other debris from damaging instrumentation components. Keep pieces of instrumentation out of welded areas. So you got section 2 review on page 28. I'm going to continue on and finish out with section 3. Section 3 goes into air and signal blowdown. So this is just cleaning out the different lines and stuff like that. Blowdown valves, should know what those are. And then a signal line using air lines for control, should know what those are. 310, systems requiring moisture removal. First sentence is highlighted. The primary reason to blow down instrument air lines is to remove any collected moisture from the lines. So you can have, there's a bunch of different ways of doing this. You can have automatic blowdowns where, like the air compressor outside here at Nunez has an automatic blowdown because we chill the air. Whenever you chill the air, drops it below the dew point, water drops out of the air. You want nice dry air for your instrument air and stuff like that. And then it has an automatic, like every every 5 minutes it blows down the line or something along those lines. You don't want that water condensating inside of your air lines and inside of your pieces of instrumentation. The next, second paragraph in 310, first sentence is the first highlight. The most significant collection point for water vapor to condense and collect in compressed air systems and is in the receivers that store the compressed air. So the accumulators that store the compressed air usually have the blowdowns on them. The immediate next sentence has two more questions that come out of it, separate highlights. As the air heated by compression cools in the receiver down to the dew point, the water vapors condense out and collect at the bottom. That's what I said. As they cool down, water vapor, the water drops out of the air, and they have to get rid of it. So it's just regular water that they're blowing out of the bottom of the lines. 320 blowing down line, 321 blowing down instrument air lines. Moving on to page 30. In between the two warnings on the left-hand side of page 30. The second paragraph, in between the two warnings, last two sentences are highlighted. If the valve were fully open, the extreme pressure drop could cause an equally extreme temperature drop. This can cause water to freeze and block the line. So whenever you're blowing stuff down, you're doing it slowly, not opening the valve full blast, because remember, temperature and pressure are directly related. I drop the pressure super fast, my temperature is going to drop super fast, and it can cause freezing. Next paragraph, first sentence is highlighted. Allow the air and water mixture to escape from the blowdown piping until all visible condensation is dissipated. So, until all the water's up, open the lines until there's no more water in the lines. Obvious enough. 322, blowing down instrument signal lines. 322. First sentence is an online test question. The procedure for blowing down signal lines is essentially the same as that for airlines, except that there is an added danger of damaging the instrument. Don't want to damage the instrument, so you're going to take a little bit more caution in blowing down these lines. The next paragraph, first sentence, is a highlight. The first consideration in the blowdown of the signal lines connected to an instrument is to determine the purpose of the instrument in the process. You never want to blow down these lines when stuff is running, because you're going to mess up the pressures or whatever these pieces of instrumentation are connected to the process. So you want to figure out what they're doing before you just go blowing them down. Page 31, first sentence on page 31, the first paragraph is highlighted. The first step after isolating the instrument from the control system is to slowly open up the equalizing valve. So you're going to shut off the two main lines, open up the equalizing valve, and then blow down, if you have blowdown valves. So you can look through. They have like the 5 valve instrument manifold, which is what we have in the lab. You might notice all theirs are capped with blue, but that center one usually has like a green tag, like in figure 27. Green represents your equalizing valve. But yeah, you want to, different colors mean different things. Like blue is usually isolation, green is equalizing, and then red is usually your blowdown. So these caps usually come in different colors. That's all my highlights for chapter or module 9 of instrumentation 2.